What's up, guys? I wanted to take some time today and talk about the ECG paper, so I hope you're ready to rumble, okay? The reason why I wanted to camp out here for today, for a couple minutes, was that as you flip through the book and as I'm showing you examples on the PowerPoints or through Google on the projector, you're going to notice that there's different types of paper that you're dealing with here, okay? In the end, they give us the same measures, they tell us the same things, only for some of us, it might be harder to interpret from one type of paper than the other. For me, for example, that was the case. I prefer one type over the other, but in the end, whatever paper we've got is what we've got to interpret from, okay? So look at these two types. We know that the heart we know that these two papers are going to give us a graphical representation with the waves added to them as far as what the heart is doing electrically. All right. The top one is called a dot matrix paper. Dot matrix. Look at it carefully. You see all those dots lining these? Inside of those big boxes, that's what they call a dot matrix. Those dots are supposed to represent the corners of the smaller boxes that were there if we're looking at something like this. Okay? So this guy down here is a lined graph paper. Both of them have their advantages and disadvantages. When you're beginning, you might need to depend a lot on these guidelines, the ones that just continuously run up and down through the paper, both thick and thin. And so that helps you out because you know exactly where the P wave is going to start, or where the PR interval starts and ends, where the QRS starts and ends, and things like that, because they're all over the place. So they give you a good guide as to where to start and end your intervals. Now, as you get more deeper into these rhythms that you're going to see here, you're going to notice that this isn't always preferable, because in some cases you might have to be squinting your eyes to find the beginning of a wave or an interval or a segment or the deflection, the height of a certain wave, okay? In which case the dot matrix comes in and it makes it just a little bit easier, okay? If you look at this paper compared to this one seems to be a little more clear. And that's a common issue, all right? For me, because I've been doing this for a couple years, I prefer dot matrix. It's a little easier on the eyes. I can identify waveforms, intervals, things like that much easier than compared to the line graph type. However, I've had a lot of students come up to me and say, "Sir, I can't do dot matrix. I just can't get my measurements right. I like the line graph paper." All right, that's fine. You know, whatever preference you have, that's good. But you'll see that that's going to slowly start to change as you get into it more and more. Okay, so in the end, guys, these two different types of paper tell us the same thing. They're just in different formats. All right. So because they tell us the same thing, we're going to focus on just one. And we know that this is a highly graphical representation of the heart, okay? So we're going to go ahead, and all I want to do for the rest of the time that we have here is just define the axes and the measures that are standard for paper when it's being printed out, okay? So let's go this way first, our horizontal. Think back to high school geometry, math, wherever you saw this stuff first. This horizontal axis is called my x-axis, okay? This x-axis is going to be a measure of time. It's going to be a measure of time. Whether it be in seconds or milliseconds, okay? Now, for me, guys, I'm going to be honest with you. I do all my measurements in seconds. That's just what I'm used to, okay? You might see me once in a while talk about milliseconds. You'll probably see in the book as milliseconds, all right? But as far as I'm concerned, I think seconds are going to be what's most commonly used here, okay? It's going to be a measure in seconds. So let's define some things, okay? If we're looking at the graph, I moved it up a little. Okay, let's look at the graph. You notice that we have a couple of small boxes. Give me a second. There you go. We have a couple of small boxes that are lining up horizontally from one bold line to the next. Okay? They're lining up. So those 5 small boxes, count them, 1, 2, 3, 4, 5, are going to be a measure of time. Each individual small box is a measure of time. Alright, so let's define what one small box is. Let's say this is a small box right there, right where I'm putting my marker. Okay, that's a small box, so I have one of those. Oh, let me get my pen tool out. So I have one small box. Is equal to 0.04 seconds. Okay, that is the measure, the length, the value of one small box. But I have 5 here. I pointed out 5 earlier. So what that's going to mean now, 1, 2, 3, 4, 5, is that if I wanted to get the value of one big box on the x-axis, I have to multiply the 5 times 0.04. So do that in your head real quick, and so that comes out to 0.20 seconds, 0.20 seconds. So I'll put it one big box is equal to 0.20 seconds in duration. Alright, I'm not going to go too much into that. There is going to be a separate video for intervals and segments and waves and how to apply that to the waves themselves that we see there. So wait for that or watch it when you get a chance. But what I do want to say with these values is that these values will remain true if the paper output, how fast the paper is being printed out, stays the same. Okay, stays standard. So I'm going to put it over here to the side. Standard paper output is equal to 25 millimeters per second. Okay, standard paper output is equal to 25 millimeters per second. If this is true, then these are going to remain true. Okay, how do you usually check this to see if it's true? Well, it usually tells you on your 12-lead printout. It'll tell you if it's printed at 25 millimeters per second nowadays with the extra data that we have at the top of the EKG. And again, that's going to be a separate video. But standard paper output is 25 millimeters per second. Okay, let's go to my second axis now. I'm going to move this up just a little bit. Okay, so now my second axis is going to be my y-axis, going up like this. So y is going to be a measure of amplitude. Okay, it's how strong the electricity was going through that area of the heart. The unit of measurement for y will be millivolts. That's a capital V. All right, it's in millivolts. So how do we define this? Well, let's look at the EKG paper. Okay, so if I just grab one small box, let's say it's that little guy right there. That one small box, whether we're going across or up and down, it's going to be the same on all sides. It'll be 1 millimeter in length. So one small box, oops, let me get my pen tool. One small box is equal to 1 millimeter. Okay? One small box is equal to 1 millimeter. Now, because the unit is in millivolts, we have to have a certain amount of millimeters to meet 1 millivolt. All right. So the standard gain setting, or the standard amplitude setting, is going to be, I'll put it up here, up top, okay? This is standard gain. I'm not sure if there's a universal sign for standard. Is going to be 10 millimeters per millivolt. Okay? So in essence, we have to have 10 small boxes to get 1 millivolt out. Alright, so 10 of these guys. So 1, 2, 3, 4, 5, making that big box. 1, 2, 3, 4, 5, making that big box. So from here, or from here to here, is going to be 1 millivolt in power, okay, in output. So why do we need to know this? If we have, for example, an athlete who is well trained, and we compare the deflection, the height of a similar person, same age, only physically inactive, you would notice that his deflection, his gain, his amplitude that he has on his QRS waves are going to be a little bit bigger, okay, because of the adaptation that his heart has needed to have in order to do the activity that he needs to do. Okay, so that gain is going to tell us, and this goes into clinical settings as well. If you have someone with left ventricular hypertrophy, well, the way you know it's hypertrophied is by a really tall wave. Okay, by a really, really tall wave. A lot of times, though, when you're printing out the paper speed, or when you're printing out the paper, the gain itself may not be on the paper, okay? You may have to kind of dig in just a little bit deeper to understand what the calibration of the gain was, because it's not always given to you in broad daylight. You have to dig in and see. So I'm going to zoom out and show you. I have a 12 lead way over here in the corner, okay? And this 12 lead is going to show you what to look for in case you're not given a calibration of gain for the gain setting, okay? So look at it carefully. You're looking at it across. We have all these lead views. If you're not familiar with these lead views, go ahead and take a look at that video as well. Okay, and if you make your way all the way about right there, let me switch my pointer over to an arrow. This guy, or this guy right here. Okay, so this is going to be my gain setting. Okay, this guy right here. If this is a standard calibration, I'm going to zoom in, he should be 10 small boxes in height, and that's going to give me 1 millivolt at the end. Okay, so what am I going to do here? Pointer. I'm going to do my little pointer. Okay, so here we go. Let's count them. It's a little blurry, I understand, but we got to work with what we have. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that does come out to 10 small boxes, which equals 10 millimeters, which equals 1 millivolt in the end. Okay, so this is standard calibration. This is 10 millimeters per millivolt. Okay, 10 small boxes in height is the standard gain setting. I'm going to move back out here. So that's what you look for. You look for this little tower that you have given to you on the EKG paper. Okay, and so that's what I wanted to talk about today, guys. I didn't want to spend too much time going into this. Very simple stuff. You have two different types of EKG paper: dot matrix, line graph paper. In the end, they give you the same readings. The x-axis is measured in time, seconds or milliseconds. One small box is worth 0.04 seconds. One big box is worth 0.20 seconds. The standard paper output and what makes these true is going to be the 25 millimeters per second paper output, paper being printed out at that speed. Okay. For the y-axis, amplitude, millivolts, Standard gain setting on the machine is going to be 10 millimeters per millivolt. So it's 10 small boxes basically in height per millivolt. Alright guys, I'll see you guys on the next section. Have a great day. God bless you all.